Good morning, everyone, and welcome to this lecture. This is lecture number 2 in EMI, and we will try to wrap up the different ways in which current can be induced. We have seen in the first class that the Faraday's law of electromagnetic induction. Do we remember?
Yes, sir.
We have seen that whenever there is a magnetic flux and it keeps on changing with time, you have an EMF induced in the coil, and that EMF is minus n d phi by dt. It is basically equal to negative of the rate of change of flux. We have also seen that this negative sign is explained by Lenz's law, which is nothing but the law of conservation of energy, which states that the direction of induced EMF is always induced whether the circuit is closed or not, but current will always only flow when the circuit is closed. Yes or no? The EMF
Yes, sir.
and the current depend on time, but the charge flown through the circuit, it only depends on the change in flux. We had also seen how we can change this magnetic flux. We can change this magnetic flux in different ways. The first way in which we had changed the flux was by changing the value of the angle theta. How did we change the value of the angle theta? We started to rotate the coil. This is the way EMF is induced in most of the cases. This is the case where we call it as periodic EMI. This is the case, this type of EMI. In some books, you will see the term periodic EMI. This is what we call it as periodic EMI, and this is how your alternating current or alternating voltage, AC voltage or AC current is produced. You just have to rotate a coil inside a magnetic field, periodic EMI. We'll now today move on and see the other two cases. How can you induce EMF or how can you change the flux? The second way of changing the flux is by changing the area of the coil. Changing the area of the coil. Now, this type of EMF which is induced is sometimes also referred to as dynamic dynamic EMF. Dynamic EMF, the EMF which is induced by actual motion, changing area. There is going to be some sort of a motion. Now, how are you going to solve questions on this? We will see it by this. A circular coil of radius r is converted to a square coil in t seconds. Find the EMF induced, current flown, and charge flown if the resistance of the coil is ohm. So I'm given this symbol for the resistance because R is used for the coil ka radius. You have a circular coil and you change the circular coil into a square coil. You take t seconds to change it. Uh, Obviously, this has to be placed in a magnetic field. So magnetic field is B. So there is a circular coil which is placed in a magnetic field. The value of the magnetic field is B. So you know how much is the magnetic field, you know how much is the radius of the coil, you know how much is the time taken to convert this circular coil into a square coil. You have to find out the current, charge, and EMF. The resistance of the coil is given as omega. Some people call it ohm. So how are we supposed to do this? We are supposed to understand that initially it is a circular loop. You have a circular loop of radius r. Now this circular loop of radius r is converted, the circular loop of radius r is converted into a square. And if I call the square side length as A, you must understand that the length of the wire remains same. When I say length of the wire, 2 pi r is the total length of the wire, that must be equal to 4a, where a is the length of the side of the square. So the side of the square becomes pi r by 2. Now if you understand this, the rest of the problem is very simple. The induced EMF is minus delta phi change in flux divided by change in time by time. Remember, here we are calculating the average EMF that has been introduced, that has been induced. The average EMF change in flux, negative sign only tells us the direction. Forget about the direction. What is the change in flux?
Sir,
There
it
is
is B.
nothing said about the angle between B and A, so we will assume that the angle between B and A is taken as 0. It should have been mentioned, but I forgot to mention it. Anyway, so angle is 0. So B is magnetic field. Magnetic field multiplied by the final area. Final area will be A square minus the initial area. Initial area is pi r square divided by T. That will be the induced EMF. You already know the value of A. You can put the value of A and you will get your answer. To get the value of current, remember this will be the average current. That will be induced EMF divided by the resistance R. Here resistance is given by omega, so E divided by omega will give you the current. To find out the charge, you just multiply this average current with time, or you find the change in flux and divide it by the resistance omega. This is how this question has to be done. It's very less likely that the question of this type would come, where they physically go and change the area of the coil, change the shape of the coil. These type of questions are not very likely to come. But you must understand that changing area means basically you are going to change the area in some way. This is one of the ways of changing the area. You change the shape of the coil, and that is how you change the area. I'll give you a minute to note this down. Then we move on to the next concept, which is known as motional EMF. Now, what is this concept of motional EMF? If you have a conductor and the conductor is placed in a uniform magnetic field, let us say you have a conductor and that conductor is placed in a uniform magnetic field. You have a conductor whose length is L, as you can see here, whose length is L, and this is placed in a uniform magnetic field, and the magnetic field, as you can see, is B, it is inside, and it is moved with a constant velocity v. Now, when it is moving with a constant velocity v, all the electrons and protons, the positive and the negative charges, are experiencing a force. Do we understand this? Yes or no? If I
Yes.
talk about the positive charges, V cross B, the positive charges are moving upwards. Do we understand this?
Yes.
The positive charges are moving upwards, whereas the negative charges are moving downwards. So the negative charge will go and deposit on the lower end, and the positive charge will go and deposit on the upper end. Do we understand this?
Yes.
Because of this positive charges going on the upper end, the positive part will be at a higher potential and the lower part will be at a lower potential. Yes or no?
Yes, sir.
Now, because of this movement of charges, an electric field would be induced in the rod, and this electric field will be moving from the positive charge towards the negative charge. Yes or no?
Yes, sir.
Because of this, because of this force, because of this force on the because of this force on the because of this electrostatic field, the protons and electrons will be experiencing force. Yes or no? The electrons will be experiencing force in the upward direction and protons will be experiencing force in the downward direction. Yes or no?
Yes, sir.
Now this force is going to be opposite to the magnetic force. So as long as magnetic force is more, the electrons will keep on moving downwards and protons will keep on moving upwards. But as more and more electrons go downward, electric field becomes more and more strong, and there would be a time when the net force acting on these bodies, the net force acting on these electrons and protons would be zero. Do we understand this?
Yes, sir.
That means the electrostatic force plus the magnetic force vectorly becomes zero. Yes or no?
Yes, sir.
That means if I write it, Q into E is the electrostatic force plus Q into V cross B is the magnetic force. That becomes equal to zero. Or a electric field is formed, and this electric field is equal to minus V cross B. Yes or no? Minus sign indicating that this electric field will be opposite to V cross B. Do we understand this?
Yes, sir.
Now, because of this electric field, a potential difference would be established between the point L and N in this. Do we understand this?
Yes, sir.
And this point L will be at a higher potential, and this point N will be at a lower potential. The small potential difference between any 2 points dV will be given by minus E dot dl. Yes or no?
Yes, sir.
From there, you can find out the potential difference between the points L and N. The potential difference between the points L and N. Which point will be at a higher potential? Which point will be at a lower potential?
L at higher potential and N at lower.
So VL minus Vn, higher minus lower, will can be written as V E dot dl ka integral. To write integral of E dot dl, we can write it as V cross B dot dl, and you understand that this rod now behaves This rod now behaves nothing but like a battery. Do we understand this?
Yes, sir.
And this battery has an EMF. And how much is the EMF of this battery? The EMF of this battery is equal to this one. Do we understand this?
Yes, sir.
This battery, this rod can now be replaced by a battery. This concept where a rod or a conductor is moving inside a magnetic field, and because of this motion, an EMF is induced in this rod. This concept is known as the concept of motional EMF. The EMF which is induced in this rod, the concept, the process by which this EMF is induced, this concept is known as the concept of motional EMF. The EMF induced in this rod is known as motional EMF. And what is the value of this motional EMF? It is V cross B dot dl ka integral, which is the higher point, which is the lower point. You find out the cross product V cross B, wherever your fingers point, that is the direction in which positive charge are going to move. That is the point which is be at a higher potential. That will be treated as the positive terminal of the battery. This rod can now be replaced by a battery. The EMF of this battery will be given by V cross B dot dl. Do we understand this?
Yes, sir.
I'll give you 2 minutes to note this down. Now remember, this EMF induced, this is given by this V cross B dot dl. Now this V cross B dot dl is known as scalar triple product. Have you heard this term, scalar triple product?
Sir.
Have you heard this term, scalar triple product?
Yes, sir.
Now there is a special thing that you have to remember about this scalar triple product. This scalar triple product becomes zero if any two vectors are parallel. Do you understand this?
Yes.
If any two vectors are parallel, the scalar triple product becomes zero. Do we understand this?
Yes, sir.
Okay, note this down. Noted it down.
Yes, sir.
Now, if all of these three vectors are perpendicular to each other, all of these three vectors are perpendicular to each other, then the EMF will be maximum and that value will be equal to VBL. Yes or no? No, yes.
Yes, sir.
If any two vectors are parallel or anti-parallel, then the EMF, there will not be any EMF induced and the value would be equal to zero. Do we understand this?
Yes, sir.
Okay, I'll give you 2 minutes to note this down. Now, keeping in mind, we have this V cross B dot dl, we can look at different cases and see how much EMF will be induced across the rod in the different cases. So let me draw these different cases. First, let me draw them, then I will give you time to note them down. What will be the EMF induced in the different cases that we are going to see? Let us take the case of the first one. This is a rod. In all the cases, the length of the rod is going to be L. So I'm just drawing it once. The length of the rod is going to be L. The velocity of the rod is going to be V, and the magnetic field will be going to be V inside A and B. In this case, as you can see, all the three length vector, V vector and B vector, all the three vectors are parallel. I can replace this rod by A battery, how does the battery look like? The battery will look like what? What will be the EMF of the battery and what will be the positive terminal and the negative terminal of the battery? Tell me. Do we
A is
understand the
positive
question?
and B is negative.
Okay. A will be positive, B will be negative. So I can replace this entire rod by this, and the value of EMF of this battery will be equal to VBL. Do we understand this?
Yes, sir.
Everyone understands this?
Yes.
Now, if I go to the second case, I will give you time to write. Just listen to me. The length is like this. If I have the velocity in this direction, or if I have the velocity in this direction, if I have magnetic field in this direction, or I have magnetic field in this direction, any of the four cases, what will be the value of the EMF induced in this rod?
0, sir.
Why 0?
Because they are parallel or anti-parallel.
So here either velocity or magnetic field would be parallel or anti-parallel to the length. Do we understand this? Yes or no?
Yes.
Now, third case. If I have magnetic field in this direction and length in this direction, or magnetic field in the outward direction, magnetic field is in the outward direction, and I have velocity also in the inward direction or in the outward direction, in this case also the magnetic field, the EMF would be 0. Do we understand this?
Yes.
So in any case where any of the vectors are parallel, the magnetic field, the EMF induced would be 0. Do we understand this?
Yes, sir.
Let me move on to the next case, case number 4. And in case number 4, what I am going to do, the length is L, magnetic field is B, but the velocity I have drawn is like this. Now in this case, which point will be at a higher terminal, which point will be at a lower potential, and what will be the potential difference? Now how do you find it? Now I'm not going to give you in terms of angle. What I'm going to do here is to resolve this V into two components. One component will be perpendicular and one component would be parallel. Which component of velocity will create this EMF and which component will not create? Tell me. What will be the value of the induced EMF across this rod, and which terminal would be positive and which terminal would be negative? Here the parallel component of velocity cannot
Sir,
create
it is
any potential difference. It's only the perpendicular component that can create V cross B. So you can see point A would be at a higher potential, point B would be at a lower potential, and the potential difference would be V perpendicular into B into L. Do we understand this?
yes, sir.
Everyone understands this?
Yes, sir.
Okay. Everyone gets this?
Yes, sir.
Anyone having any doubt?
No, sir.
Okay. Let me see the next one. Let us imagine that I have a semicircular loop. Oh, let me take it this way. I have A closed loop. I have a closed loop which is placed in a magnetic field B and which is moving with a velocity v. Closed loop. What will be the EMF induced in this loop? Will there be any EMF induced in the loop?
Yes.
How much will be the EMF induced in this loop? Well, there will be no EMF induced in the loop. We have seen that closed loop placed in a magnetic field moving. It will not be any loop. Now, I can use this and do some very important results. The first result I can use it is if I have a semicircular loop. If I have a semicircular loop of radius r moving with a velocity v in a magnetic field B. Now, if I close this entire loop, the EMF would be zero. That means to find out the value of EMF induced between the ends AB, what I need to do is I need to close it. Whatever EMF is induced in the left part, the same EMF will be induced in the right part. The EMF induced in the right part AB will be equal to V cross B. So I can write this in this fashion. How I can write this in this fashion? A term will be positive, B would be negative, and the induced EMF will be V into 2R into B. Do we understand what I have done here?
Yes, sir.
If I have a random shape loop, if I have a random shape loop AB, again it should not be a closed loop, and then I know the length of this line is L and it is moving with a perpendicular velocity v in a magnetic field B, then I can replace this loop by a battery, and the battery will look like this A into B, and the EMF of this battery will be equal to VBL. Do we understand this? Do we
Yes, sir.
understand this?
Yes.
Everyone understands this?
Yes, sir.
I make the most general case, and in the most general case, the loop is like this, and the velocity is not perpendicular. Velocity is not perpendicular, so I can break it up into two components, V perpendicular and V parallel. I can replace this by V perpendicular B into L. Have we understood what I have done here? Yes or no?
Yes, sir.
I'll give you 2 minutes to note this down. So now you can answer these questions. Question number 1. In this case, what is the EMF induced, which is at the which point is higher and which point is lower? In this case, and what is the EMF induced?
Sir, L will be at higher and N will be at lower.
And what is the EMF induced?
BV2R.
VB into 2R. Do we understand this?
Yes, sir.
What about this case? This is a question taken from SCV. Which end is higher, which end is lower in this case?
Sir, X is at higher and Y is at lower.
Okay. What is the potential difference between X and Y?
Sir, it is BV into 2L sin theta.
You have to find out the potential difference between this point L and this point N, not between X and Y, between L and N.
Okay.
Between X and Y, what is the potential difference?
It is BV2L sin theta, sir.
What is the potential difference between L and N?
Same, sir. Same or different? Okay. It is also
Vx minus Vy is 2VP L sin theta. VL minus Vn is equal to 2VBL into 1 plus sin theta. This L and this L also create potential difference, my dear friends. Do we understand this?
Yes.
Do we understand this?
Yes, sir.
So that is the reason. Next one, this one. What is the potential difference between L and N? What is the potential difference between L and N?
0, sir.
0. Why 0? Why it is 0?
V is 0, sir. V perpendicular. V perpendicular is 0, sir.
Okay. This one then. Between L and N, what is the potential difference? I put 2 more rods here. What is the potential difference between L and N? Yes,
0, sir.
0, sir. Do we understand this?
Yes, sir.
It is going above our head saying bye bye.
We understood.
What about this one, the next one? What is the potential difference between L and N?
0, sir.
Are we able to understand this?
Yes.
This one. What is the potential difference between L and N?
BV3L, sir.
BV3L. This one. What is the potential difference? What is the EMF induced in the loop? EMF induced in the loop.
0.
Answer is
0.
this one. EMF induced in the loop.
0, sir.
Are we able to understand what I am saying here?
Yes, sir.
This one. EMF induced in the loop. Triangle one.
Zero.
So the answer is 0 in all these cases. Do we understand?
Yes.
Or it has gone above our head saying bye bye?
No, sir.
What? No, sir. Have you understood this?
Yes, sir.
Now remember the heading of this topic was EMI due to change in area. Now you don't see any change in area here. What we have seen is we just had a rod and we were moving it inside a magnetic field. Where does area come? Now if I just get you the diagram like this, then probably things will start to make sense. That now if I close this, if I close this by a circuit, by this rod by a circuit, then it will start to make sense how is the area changing. So now I have a rod AB of length L moving with a velocity V in a magnetic field B, which is inside. Now because of this rod moving inside this magnetic field, an EMF will be induced in the rod, yes or no?
Yes.
Now this circuit is complete, so a current will flow in the rod, yes or no?
Yes, sir.
Now you can see, you can find out the direction of this induced current by different ways. For example, you can replace this rod. You can replace this rod by a battery. How does the battery look like? If I replace this rod by a battery, how does the battery look like? The battery will look like this, yes or no?
Yes.
How will the current flow in this battery? The current will flow like this, yes or no?
Yes, sir.
You could find out the direction of this current in a different way. Now, if you look at this loop, is the area of the loop, ah, is there a flux linked with the loop? Is there a flux linked with the loop?
Yes, sir.
Is the flux linked with the loop changing with time? Is
Yes,
the
sir.
flux linked with the loop changing with time?
Yes, sir.
Is it increasing with time or is it decreasing with time?
Increasing with time.
Why it is increasing with time? Because the area of the loop is increasing with time. Do we understand this?
Yes, sir.
So I need to decrease the flux. To decrease the flux, I must create field in the forward, in the outward direction. If you find it out by this way also, the current in the loop will be anti-clockwise. So this is the case wherever you have area changing like this by a rod which is moving. We are not going to solve it from the concept of that. We are going to solve it from the concept of motional EMF. We are going to treat it as a battery. What is the EMF of this battery? The EMF of this battery will be VBL, yes or no?
Yes, sir.
So EMF of this battery is VBL. What will be the current I that flows in this circuit? It will be equal to VBL by R. Do we understand this?
Yes, sir.
Now, because of this current flowing in this circuit, this AB wire becomes a current carrying wire placed in a magnetic field, yes or no?
Yes, sir.
So this current carrying wire will experience a force, magnetic force, and if you find out the direction of that magnetic force, current I is going like this, V is like this, the magnetic force will be in the backward direction, yes or no?
Yes, sir.
This magnetic force will be equal to I into L into B, and if you find out that value, it will be equal to this one. The magnetic force will be equal to this one, yes or no?
Yes, sir.
If I want to move this wire with a constant velocity, if I want to move this wire with a constant velocity, An equal and opposite force has to be applied to the conductor. Yes or no?
Yes, sir.
How much will be that equal and opposite force? That equal and opposite force has to be same. Yes or no?
Yes.
So that force which is applied, this green force which is applied, will be again equal to this one. Do we understand this?
Yes, sir.
First listen to me, then I will give you time to note this down. So what is the power that I am giving it to you? I am giving it to the rod, that will be equal to F into V. Yes or no?
Yes, sir.
Now, this is also a circuit which has a current. Wherever a circuit has a current and has a resistor, this power is dissipated in the form of heat. Yes or no?
Yes, sir.
And what do we see here? The power which is applied is same as power which is dissipated. This is basically nothing but the law of conservation of energy. Whatever energy I am applying to move this rod, the same energy is going in the form of heat. So these are the questions that we might encounter in such cases. Do we understand this? That
Yes,
means
sir.
any question which comes like this, where a rod is moving, we will convert that rod into a battery and then we will solve the circuit with the battery on. Do we understand this?
Yes, sir.
Give you 2 minutes now to note this down. What are you doing? Where your shoes? ट्रेन आ रही है इसको मना कर लो कि आ जाए Just are we trying or shall I do it?
Where it is 1.5 into 10 power minus 4 divided by 8.
Which case? Time 2 seconds or 10 seconds? You are giving the answer after so much 1 hour and that too wrong answer.
Sir, at time 2 seconds is 3 into 10 power minus 4. And at 10 seconds, it is 1.5 into 10 power minus 4.
So at time 2 seconds, where would the loop be? The loop would be in a position where some part of the loop is inside and some part of the loop is outside. Do we understand this?
Yes, sir.
What, sir? Then there will be EMF induced in the loop. If I just draw the diagram again, it might not look very enticing here. At time 2 seconds, some part of the loop is inside and some part of the loop is outside. The loop is something like this. There would be EMF induced in the loop. What would be the EMF induced in the loop? The EMF induced in this part is 0. The EMF induced in this part is 0. The only EMF is induced in the vertical part. How much is the EMF induced in the vertical part? V into B into L. V into B into L. And what is the current? V B L by R. Oh, you don't have to find out the current. You just have to find out the value of induced EMF. VBL is the answer. You cannot multiply V with B with L. Shame on you. The answer that I have is 3 into 10 raised to the power of minus 4 volt. That is the answer I have. I don't know whether it's correct or not. At 10 seconds, at 10 seconds, at 10 seconds, the entire loop is inside. Like this. Because it is 20 centimeters long. At 10 seconds, it is somewhere in between. The average
Yes.
EMF, the total EMF induced in the loop is 0, my dear friends. So the answer for the first case is 3 into 10 raised to the power minus 4. And answer for the second case, I don't know what you were doing. The answer is 0. I'll give you 2 minutes to think about it. If you have not understood it, ask me. I'll give you 2 minutes. Then we have this question, my dear friends. A rectangular loop of side 10 centimeter and 3 centimeters moving out of a region of uniform magnetic field, 0.5 Tesla directed normal to the loop. If we want to move the loop with a constant velocity of 1 centimeter per second, what is the mechanical force required to do it? Yes, the answer is?
2.25 into 10 power minus 3.
Yes, B V square L square by R. Yes or no?
Yes, sir.
You can use this and get the answer. Okay, I think we have done this. Let now I will give you this question. Now you must understand what is the difference between this one and the previous ones. So do it fast. I'll give you 5 minutes. A rectangular loop of wire moves away from an infinite long wire carrying current I. Find the EMF induced in the loop. In this case, where the distance of the loop from the wire is x. Let me see if you can do this. Otherwise, I will break this up into smaller questions. Let me give you a chance. Now, if it was a square loop or any closed loop placed in a uniform magnetic field, it was a closed loop placed in a uniform magnetic field, what was the EMF induced in the entire loop?
0.
Yes? Can you hear me, beta?
It is 0, sir.
Now, let us try to understand why it is 0. Let us imagine that this loop is moving with a velocity v like this. Yes or no? And the magnetic field is inward. Now, how is the magnetic field induced in the loop is 0? We understood it from one way, that there is no change of flux. Remember that question where the loop was moving in and out of the loop? Do we remember that question?
Yes, sir.
Now I'll try to make you understand in a different way. I can convert A, B, C, D, the different wires into batteries. What will be the EMF induced in the battery, induced in the wire AB? What will be the EMF induced in the wire AB? What is the EMF induced in the wire AB? What is the EMF induced in the wire AB? We don't know this. Well done. It is 0 because the length of the wire is parallel to the magnetic field. Similarly, the EMF induced in the wire CD would be 0 because here the length is opposite to the to the velocity v. Scalar triple product. Obviously, you have forgotten it. Just 10 minutes before we studied it. Anyways, so the EMF induced in the individual wires AB and CD is 0. Now, if I talk about the EMF induced in the wire BC, the EMF induced in the wire BC, if I take the length of this side as L, the EMF induced in the wire AC will be VBL, and it will be like this. C will be positive and B would be negative. Similarly, if I look at the EMF induced in the wire DA, it will again be same VBL, and the battery will also be put like this. So if I take the entire loop, in the entire loop, the net EMF, both the batteries will cancel each other out. The net EMF would be 0. And that is how you can understand this thing in this way. Instead of taking it as flux changing or flux not changing, you can convert all the 4 wires into current carrying into conductors, and you can convert them into batteries and see how much is the EMF induced in the battery. Now coming to this question, now what is the difference between the question that I have done and the question which is there?
B is uniform, sir, in this question.
In the question that I have done, B is uniform, but the question which is I have given, B is not uniform. B is not uniform because It is produced by a infinite wire. Do we understand this?
Yes.
B is produced by an infinite wire, and that is why it is not uniform. If B is not uniform, the batteries in both the parts will not be same. They would be different, and that is why you will have an induced EMF in the loop. Anyways, what I'm going to do is again break this question into small parts. Break this question into small parts. Let us say that this is your infinite wire. This is your infinite wire carrying current I, and this is the wire AB. And the wire AB moves like this. Wire AB moves like this. And I ask you, what is the EMF induced across this wire AB? What will your answer be in this case? The wire is like this and I'm moving it like this. What will be the answer?
0, sir.
Why 0?
Perpendicular velocity is 0.
Because the length is parallel to V. If any of the two vectors are parallel, the scalar triple product becomes 0. Anyways, if I make the velocity inside like this, and then I ask you the same question, what is the EMF induced in this wire AB? What is your answer? If the velocity is inside,
0, sir.
why it is 0 now?
V is parallel to B.
V is parallel to B. So in both the cases, EMF induced will be 0. Do we understand this?
Yes.
Do we understand this, everyone?
Yes, sir.
In only one case, EMF would be induced, and that case would be when V is like this, or it is at an angle like this. Yes or no?
Yes, sir.
Now, in this case, the problem would be that this wire will be placed in a non-uniform field, so you could not put the formula. We have to do it by the method of integration. I don't want you to get into that method of integration. What you will do is, you will just remember this formula that I am giving you and use it wherever this question comes. So when this is moving perpendicular like this, the answer is mu naught IV by 2 pi ln of L plus A upon A. Now you will see, you will ask what is A and what is L. This is A and the length of this wire is L. Now remember, if this velocity is not perpendicular, if it is at an angle, you can take the perpendicular component V perpendicular. Do we understand this?
Yes.
So this is the answer in this case. I'll give you 2 minutes to note this down. Now let me change this question and let me make the current carrying wire like this, and let me put this wire like this, AB. If I move the wire like this with a velocity V, what will be the induced EMF across this end? What will be the EMF induced across the ends of the wire?
0, sir.
Why 0?
Velocity is anti-parallel to.
Okay, parallel or anti-parallel. If I move it like this, then if I move it inside like this, then
0, sir.
why 0?
It's parallel to length.
Is parallel to length. Only in one case you will have this when this moves like this. If I say that the distance here is A and the length of this wire is L, can you tell me what will be the induced EMF across the ends in this case? Now, even though this wire produces, even though this wire produces Non-uniform magnetic field, but from A to B, is the magnetic field uniform or is the magnetic field non-uniform?
Uniform.
Uniform. So the answer is still remain uniform. So what will be the induced EMF across these two ends? You can see magnetic field is going inside, yes or no?
Yes, sir.
Magnetic field is going inside. V cross B. So which point will become higher potential? Point A will become higher potential, yes or no?
Yes, sir.
Point B will become lower potential, yes or no?
Yes.
And the EMF induced will be equal to VBL, where what will be the value of B? What will be the value of B? B is the magnetic field produced by an infinite wire. Do we understand this?
Yes, sir.
What is the value of magnetic field here? Mu naught I by 2 pi A. Yes or no?
Yes.
Do we understand this? Yes,
Yes.
or no?
Yes, sir.
Having understood all the three cases, can you now solve this question? Yes or no?
Yes.
I'll give you 2 minutes to try it. Let me know once you are done. If you cannot do it, let me know also. So that is correct. Basically, what you have to do here, I have to move to a different page. So basically, you can replace this wires like this. Yes or no?
Yes.
This nearer wire, the magnetic field is mu naught I by 2 pi x. Yes or no?
Yes, sir.
And this wire, the magnetic field is mu naught I by 2 pi into L plus x. Yes or no?
Yes.
Which field is more? This field is more. Yes or no?
Yes, sir.
So you have to subtract the other field from this field and you will get your answer. I think the answer that you are going to get is how much? Mu naught I by 2 pi into x into L plus x. And on the top, L will remain. Yes or no?
Yes.
Into V into L, I think, right? VBL, right? Do we understand this?
Yes.
Everyone understands this?
Yes.
Everyone understands this? Yes or no?
Yes, sir.
I'm not getting voices. We understand this, yes or no?
Yes, sir.
Now, if I have this entire loop moving like this, then what is the answer? What is the EMF induced in the loop?
Zero.
Zero. You can think it of in many ways. The first way is this loop is moving like this. The flux does not change, yes or no? Because
Yes.
in this region, this magnetic field does not change. The flux does not change. Do we understand this?
Yes.
That is one way of doing it. Or you can convert it into wires. The EMF induced in this wire would be zero, yes or no?
Yes.
The EMF induced in this wire would be zero, yes or no?
Yes.
EMF would be induced in this wire and this wire, but both will be equal and opposite, yes or no?
Yes, sir.
So the total EMF will be zero, and that is why the answer would be zero. Do we understand this, what I am saying?
Yes, sir.
Yes or no?
Yes, sir.
Pakka?
Pakka.
If I make the question like this, it is given a velocity v like this at some angle, let us say theta, then what will be your answer? Then what will be your answer? Then what will be your answer? I'll give you 2 minutes to think about it. Well done. I hope you understand that you just have to break it up into two components. One component would be like this, that will be v sine theta, and one component will be like this, v cos theta. Because of this component v sine theta, the induced EMF would be 0. We understand this?
Yes, sir.
The only EMF will be due to this component, yes or no? And this is now this question becomes same as the previous question.
Yes.
This one, yes or no?
Yes, sir.
We just need to replace this v by that v sine v cos theta component, and we are done. Do we understand this, or this has gone above our head? Saying bye bye, bye bye, sir. I'm going bye bye, bye bye, bye bye.
We got it, sir.
Everyone understood this? Everyone has noted this down?
Yes, sir.
Yes or no?
Yes.
We move on to the next heading. EMF induced due to rotation. Rotation of rod. Up till now, the rod was in translational motion. What happens if it is rotating? What happens if it is rotating? What happens if it is rotating? For example, you have a rod like this, center O, length of the rod is L, magnetic field is inside, and it is rotating with an angular velocity omega. Now again, I will not go into the theory of this. Let us call this point as A. Because of this rotation, every point will have velocity, but the velocities will be different. Yes or no?
Yes.
EMF would be induced in this rod. Which point will be higher and which point will be lower? If I take any one of the points, the velocity is like this. Yes or no? All the velocities are different. The velocities are like this. So V, B, you can see which point will be at a higher potential. Which point will be at a higher potential? Point O will be at a higher potential compared to point A. Do we understand this?
Yes.
And what is the potential difference between the two ends? It will be equal to half B omega L square. So remember this, the center will always be at a higher potential compared to the point on circumference, wherever that point is. Remember, if this is the case, center is at a higher potential. If you reverse the case, the center will be at a lower potential. Do we understand this?
Yes, sir. Yes, sir.
Potential difference between O and A would always be equal to half B omega L square. Everyone understands this, yes or no?
Yes, sir.
So you can replace this rod by a battery, and then once you replace this rod by a battery, the question becomes simple. Do we understand this?
Yes, sir.
Okay, now similar to this rod, if it is rotating, you could have a disc or a ring which is rotating. This is a ring. This is a ring. This is a ring rotating with an angular velocity omega. Magnetic field is inside. Now, this rotating with an angular velocity omega, this is point A here. This is point B here. This is point C here. This ring is rotating with an angular velocity omega. The radius of this ring is R. What is the potential difference between O and A, and which point is at a higher potential? Or between O and B, which point is at a higher potential? Or between O and C, which point is at a higher potential? So VO minus VA will be same as VO minus VC, and this will be same as VO minus VB. Do we understand this?
Yes.
And all of this will be equal to half B omega R square. Do we understand this?
Yes, sir.
Everyone understands this?
Yes, sir.
One more thing. Now, if in place of a ring you have a disc of radius R, and then you have points A, B, C, D. In this case also the answer remains same. Do we understand this?
Yes, sir.
Also, all points on the circumference will be equipotential. Matlab, there will not be any potential difference between any point on the circumference. Do we understand this?
Yes, sir.
Everyone understands this?
Yes, sir.
I'll give you 2 minutes to note this down. Then this is a question. A rod of length 2L is rotating about 1 and P in a uniform magnetic field which is perpendicular to the plane of rotation of the rod. M is the midpoint of the rod. Find the induced EMF between M and Q if the induced EMF between P and Q is 100 volt. Give you 2 minutes to give me the answer. So, potential difference between P and Q. Which point will be at a higher potential? Which point will be at a lower potential? Between P and Q, which point will be at a higher potential? Which point will be at a lower potential?
P will be higher.
Vp minus Vq will be equal to how much? You don't remember the formula? Well done. Half B omega into the length square. Length is 2L square. That is the potential difference between point P and point Q. What is the potential difference between point P and point M? Half B omega into the length is L, so L squared. So if I have to find out the potential difference between M and Q, which point will be at a higher potential, M or Q?
M, sir.
M will be at a higher potential. So potential difference between M and Q will be equal to what? Will be equal to how much? You can subtract this, yes or no?
Yes, sir.
This will be equal to 3 by 2 B omega L square, yes or no?
Yes, sir.
Do we understand this, or this is going above our head saying bye bye?
We got it.
So I can write it like this: 3 by 4 into half of B omega into 4L square, that is equal to 100 volt. So the answer would be 75 volts. Do we understand this?
Yes.
This entire value is this one. Do we understand this?
Yes, sir.
Yes or no? No or yes?
Yes, sir. We understood.
Thank God. I'll give you 2 minutes to note this down. Everyone understands this?
Yes, sir.
Okay, then. We can do one more question on this. This is the question. You have a pure rolling. A question of pure rolling. I hope you remember what was pure rolling. Do we remember what was pure rolling?
Yes, sir.
Hang on. Pure rolling. A disk is in pure rolling with an angular velocity omega. There are 4 points that I have marked on the disk. What are the 4 points that I have marked? It could be a disk, it could be a ring. What are the 4 points that I have marked? O, A, B, C. Do we see this?
Yes, sir.
What is the potential difference between O and A, O and B, O and C? What is the potential difference between A and C? What is the potential difference between A and B, B and C? So if you understand any one question, you would be able to solve any question that comes in this category. I'll give you 2 minutes to think about it. Do you understand? If you find out the potential difference between any 2 points, between O and A and O and B and O and C, you will be able to find out the all of the things. Yes or no?
Yes, sir.
I'll give you 2 minutes. Okay, so this is pure rolling. So pure rolling can be broken up into 2 components. You can take it as combination of rotation about the center of mass. So you can assume this to be consisting of 2 things. One, because of what I'm doing here. So I can break it up into 2 like this. Center O, radius R. It is rotating with an angular velocity omega, and this is in pure translation with a velocity omega into R. Do we understand this? Do we remember this about pure rotation, pure rolling? Do we remember this? Are we there in the class? Are we there in the class? Anyone? I think I've lost contact. Let me know once you are there, beta. Okay, so This is point A, this is point B, this is point C. This is point A, this is point B, and this is point C. Now what we are going to do is we are going to overlap both of these things together. We are going to find out the potential difference between different points because of pure rotation. Because of pure rotation about O, VA will be equal to VB will be equal to VC. Do we understand this? Yes or no?
Yes.
Then because of pure rotation, which point will be at a higher potential? O will be at a higher potential or A will be at a higher potential?
O will be at higher potential.
A will be at a higher potential. VA minus VO will be equal to half B omega R square. Do we understand this?
Yes.
That will also be equal to VB minus VO. That will also be equal to VC minus VO. Do we understand this?
Yes.
Now, because of pure translation, we can assume that OA is a rod of length r moving with a velocity omega r. Do we understand this?
Yes, sir.
Now, because of this, it is moving with a velocity omega r like this. V cross B, O will be at a higher potential and A will be at a lower potential. Do we understand this?
Yes, sir.
Then we can find out potential difference between O and A. What will be the potential difference between O and A? VO minus VA will be equal to B into omega R into R. Yes or no?
Yes, sir.
Potential difference between O and B. For O and B, the rod will be, the velocity will be parallel, so they will be at the same potential. Do we understand this?
Yes.
Now between O and C, C will be at a higher potential. Yes or no? So VC minus VO will be equal to B into omega R into R. From here, you can also understand, find out the potential difference between any 2 points. Do we understand this, how I have done this?
Yes, sir.
Everyone understands this?
Yes, sir.
Or if you don't want to do this much, you remember pure rolling can be taken as pure rotation about the point A. Yes or no?
Yes, sir.
Pure rolling can be taken as pure rotation about the point A. Yes or no?
Yes, sir.
Now, taking it as pure rotation about the point A, you can find out the potential difference between A and any point. Because of pure rotation about the point A, it is moving like this. So you can take it as a rod moving like this. V cross B, O will be at a higher potential and A will be at a lower potential. Yes or no? So
Yes, sir.
VO minus VA will be equal to half into B into omega into R square. You look at these two results, and once you add these two results, you will get the same one. Do we understand this?
Yes, sir.
To find out the potential difference between C and A, C will be at a higher potential, A will be at a lower potential. VC minus VA will be equal to half B into omega, the distance, the radius will be 2R square. Yes or no?
Yes, sir.
You find it out from here. You will also get the same result. Do we understand this?
Yes.
Now, between A and B, the distance is root 2r. Yes or no? So, VB minus VA will be equal to half B omega into root 2r squared. If you find it out from here also, you will get the same result. Do we understand this?
Yes, sir.
Everyone understands this?
Yes, sir.
Pakka? I'll give you 2 minutes to note this down. Then we come to the last part of inducing EMF, and that is changing magnetic field with time. Changing magnetic field with time. How can you induce EMF? Well, now, whenever you change magnetic field with time, the phenomena, whenever magnetic field is changed with time, first listen, then write. Whenever B is changed with time, it gives rise to an electric field. That is changing B magnetic field with time produces an electric field. This electric field is known as induced electric field. So in wherever space, in whatever space you have a changing magnetic field with time, that changing magnetic field with time will produce an electric field. This electric field which is produced by a changing magnetic field is known as an induced electric field. Do we understand this?
Yes, sir.
Now, what are the properties of this induced electric field? This induced electric field is non-conservative in nature. This induced electric field, it is non-conservative in nature. That means if you move around in a closed loop in this electric field, it will not be equal to zero. In fact, it will be equal to the induced EMF. In normal electric field, up till now, whatever electric field we have seen, let us not call it as electric field, we must call them as electrostatic field. Now, those electrostatic field was produced by electrostatic charges. That field was conservative in nature. In that field, if you move around in a loop, the line integral of electric field or change in potential was zero. Do we understand this?
Yes, sir.
Here, if you move in a closed loop, the change in potential E dot dl is not zero. In fact, it is equal to the induced EMF in the loop. Do we understand this?
Yes, sir.
Being a non-conservative field, there is no meaning of potential in this field. Potential, you cannot define potential for this field because why? Because if you move in different paths, the change in potential will be different. Do we understand this?
Yes, sir.
I'll since the space is gone, I will stop here. You can note this down, then we will move further. Okay. So this is a non-conservative field, and since it is a non-conservative field, potential has got no meaning for this field. This field is different from the electrostatic field which is produced by electrostatic charges. Do we understand this?
Yes.
Now, if you have a charge placed in this field, F is equal to QE is still valid. Remember, it's an electric field. It is different from the field which is produced by electrostatic charges, but it's still an electric field. Do we understand this?
Yes, sir.
This field can vary with time as well. This field can vary with time as well. Do we understand this?
Yes, sir.
Okay, remember it's a non-conservative field. So if you move in a loop, the work done is not equal to zero. Do we understand this? If you
Yes.
move in a loop, the change in potential is not equal to zero. If you move in a loop, the electrostatic field, the line integral is not equal to zero. It's not equal to zero. Do we understand this? If you move in a loop, the work done is not equal to zero. Change in electrostatic potential energy is also not equal to zero. In fact, the potential difference will be equal to minus d phi by dt, or integral of E dot dl will be equal to minus d phi by dt. Do we understand this?
Yes.
One more point, I will write it here. Potential or work done depends on path. Do we understand this?
Yes.
Work done by this electric field or against this electric field depends on path. Do we understand this?
Yes, sir.
I'll give you 2 minutes to note this down. Okay. So, in this case, how will you find out the induced EMF? Induced EMF in this case will be again given by minus d phi by dt. Yes or no?
Yes.
That can be written as minus d by dt into b into a into cos theta. Yes or no?
Yes.
Where a will be the area of the coil. Remember, area of the coil is not going to change. Theta is the angle between the coil and the magnetic field. Remember, that is also not going to change. What is going to change here?
Magnetic field.
So you can write it as a cos theta, and in most of the cases theta will be equal to 0 or 180. Minus sign only indicates the direction of magnetic field into dB by dt. This is how you can find out the EMF induced in this case. Do we understand this?
Yes.
How will you find out the direction of the electric field? Again, you can use Lenz's law, and that is how you can find out the direction of current in the loop. Do we understand this?
Yes, sir.
Okay, now I'll make a question and let us see if you can solve this question. I have, let us say, a square loop. It is placed in a magnetic field B, and the rate at which the magnetic field is changing is given as alpha, and this rate is greater than 0. I hope you understand the meaning of the terms that I've written. Yes or no?
Yes.
Area of the loop is A, and the resistance of the loop is R. Area of the loop is A, and the resistance of the loop is R. You have to find out in this question, number one, the EMF induced in the loop, the current flowing through the loop as a function of time. What is the current in the loop, and what is the direction of current? Can you tell me the direction of current first? What will be the direction of the current in the loop? What will be the direction of current in the loop?
Clockwise, sir.
Why clockwise, sir? Why clockwise, sir? Give me a reason of why clockwise. It will be anti-clockwise. Obviously, if not clockwise, it is going to be anti-clockwise. Can you make me understand why it is anti-clockwise? Well, the magnetic field is inside and it is increasing with time. Flux is increasing with time. I will have to decrease the flux. To decrease the flux, I'll have to create magnetic field in the outward direction. If I have to create magnetic field in the outward direction, the current would be anti-clockwise. Now, if you can tell me what is the induced EMF and what is the current, I'll give you 2 minutes. So the induced EMF in the loop, I already know the direction. Area of the loop is a square. Cos theta is 0, theta is 0, so cos theta is 1. dB by dt is given as alpha, so the EMF induced in the loop is equal to a square multiplied by alpha. To find out the current in the loop, it will be equal to a square alpha by r. These are the two questions, these are the two answers that I was looking forward. Do we understand this?
Yes.
Okay, well done. I'll give you 2 minutes to notice. Now, if I have a loop, a square loop of length L placed in the place with an infinite wire like this. Now remember, we have already found out the EMF induced in the loop when the loop is moving with a velocity v. Do we remember that?
Yes, sir.
Everyone remembers that? Yes or no?
Yes, sir.
Pakka?
Yes.
Okay. Now, if just for the, I'm taking it as a square loop, it could have been a, let me make it more general. Let me make the loop not as square loop but as a rectangular loop. So you get this as L and this as B. L as the length and B as the breadth. Okay. Now, if anyone asks you what is the flux flown through this loop, how much flux? Remember, this is a loop placed in a non-uniform field. How much is the flux through the loop? If someone asks you this question, remember the flux through the loop. The flux through the loop will be given by which formula? Mu naught I by 2 pi x into x plus L. Remember, we are talking about the flux. The flux through the loop. Why I'm writing x and x plus L. Remember this formula into B into log of A plus L divided by A. This is the magnetic flux which is linked with the loop. If a question comes, you can directly note down this answer. Do we remember this? Can we remember this?
Yes.
Okay. Now, if this current in this loop is varying as a function of time, you can find out the EMF induced in the loop. D phi by dt, I am not putting the negative sign. Negative sign only tells us the direction. So I can write it like this: mu naught B by 2 pi ln of A plus L by L, everything multiplied by di by dt. Do you understand? Di by dt, the only thing that is changing here in this question is current. Because of the change in current, there will be a change in magnetic field, and because of change in magnetic field, EMF will be induced. It is induced because of induced electric field. So you just remember these two formulae. I'll give you 2 minutes to note them down. Have you understood this? Remember, the loop is not moving, only current in the wire is changing. Do we understand this?
Yes, sir.
Then we come to this last part of this particular thing. Now, most of the cases, wherever you are going to get questions on this changing magnetic field, the magnetic will be changing in a cylindrical space. You will have a cylindrical space, and here the magnetic field would be, changing. Do we understand this? So most of the questions that you are going to encounter in this particular section would be of magnetic field which is changing in cylindrical space. Do we get this?
Yes, sir.
Now, in this particular case, because of the symmetry of the diagram and the symmetry of the question, the electric field which is induced in this cylindrical space because of changing magnetic field, it would be moving in concentric circles like this. It will be moving in concentric circles like this. And if the magnetic the direction of the field, whether it is moving clockwise or anti-clockwise, it depends on the direction of magnetic field, and magnetic field, whether it is increasing or decreasing. Here I have assumed that the magnetic field is inside, and dB by dt. What is dB by dt? What is dB by dt?
Change in magnetic field with time.
The rate at which the magnetic field is changing, I am assuming that it is greater than 0. That means magnetic field is increasing with time. If magnetic field is increasing with time and it is going in the inward direction, I have to decrease the flux. Therefore, the electric field will be moving like this in concentric circles. Do we understand this?
Yes.
Now, how can you change this magnetic field in this cylindrical space? You can have a solenoid. What is the magnetic field inside a solenoid?
Sir?
What is the magnetic field inside a solenoid? B is equal to mu naught Ni was the magnetic field inside a solenoid. You can change the current in the solenoid. If you change the current in the solenoid, the magnetic field inside the solenoid will also change, and you will get a question of this type. Do we understand this?
Yes, sir.
Give you 2 minutes to note this down. Then we come to the last part where we find out the value of this electric field. Remember, this electric field is moving in concentric circles. Do we remember this? Do we understand this?
Yes.
Now, when you take any point inside this cylindrical space, the electric field is moving in concentric circles, and the value of this electric field is, instead of remembering it like this, you should remember it like this. E will be equal to R by 2 into dB by dt. Here I have taken dB by dt as alpha. So if dB by dt is given as alpha, your final answer becomes R by 2 into alpha. Do we understand this?
Yes, sir.
If dV by dt is not a constant, then R by 2 will be, then E will be equal to R by 2 into dV by dt. Do we understand this?
Yes, sir.
You can see here this E is directly proportional to R, this graph. At E is equal to R, it becomes R by 2 into alpha. Do we understand this?
Yes.
For points which are greater than R, outside the cylinder, it becomes E becomes alpha R square by 2R. If you want, you can remember it in this fashion. R square by 2R into dB by dt. So as you can see, if dV by dt is constant, electric field will be inversely proportional to R, and you get this graph. Do you remember this graph? Has this graph come before? Has this graph come before? Please note this down. You don't remember where this graph has come? Similar graph? Okay, then that brings us to an end of this class. We are done with your EMI as such, In the next class, we will move into the concept of inductors, and we'll see what are inductors. We have already seen the first element of a circuit, capacitor, stores electrostatic energy in the form of electric field, Q square by 2C or half CV square. We have also seen resistor, energy is dissipated in the form of each. Power is I square R, energy is I square R into T. We have seen electrostatic field. We have seen magnetic field in this chapter. So in the next topic, we are going to see the third element which stores energy in the form of magnetic field or magnetic energy. And that is your inductor. So we'll see it in the next class, and we'll try to wind it up in the next class only. So be ready. Are you trying the questions that are given in the exercise that I have sent you?
Yes, sir.
If you even do even 10 or 15 or 20% of that question, that will be good enough for you to solve any question in the exam. So I'll take your leave, and we'll meet tomorrow in the next class. Take care. God bless you all.